Welcome to part 4 of the Industrial Data Management series. As we navigate the advent of smart manufacturing, data modeling emerges as a pivotal factor, enabling seamless interoperability across the entire manufacturing ecosystem. Crafting custom data models for specific use cases and applications, as we have shown in part 3 of this series, can certainly be effective. However, there are situations where utilizing a standardized data modeling approach proves advantageous. This approach fosters interoperability throughout the whole manufacturing ecosystem, encompassing not only your operations but also extending to suppliers and customers. This video explores the world of data modeling standards. We will delve into 4 such standards, detailing how they enable interoperability through data modeling. Our comparative analysis will provide insights into their unique purposes and overlapping areas, guiding you to the standard best suited for your needs, thereby fostering a smart manufacturing success for your organization. If you would like to watch the whole series on industrial data management, subscribe to our channel. Okay, let's get us started with part 4. Digital Twin Definition Language, known as DTDL, is a language for creating models for digital twin use cases. It allows manufacturers to capture the rich semantics of their IoT solutions, including the relationships between different devices, their properties, commands, and telemetry. DTDL's relevance for smart manufacturing lies in its support for the creation of highly interoperable and scalable digital twins. These twins can model all elements of a manufacturing line, from individual machines to the whole factory, offering a comprehensive and real-time overview of operations. The DTDL language follows JSON syntax but is based on JSON-LD. JSON-LD, or JSON for linked data, is a method for encoding linked data using JSON. It is a World Wide Web Consortium W3C standard that provides a way to enrich your data by contextualizing it with schemas or vocabularies that you choose. This makes it easy to define complex models and relationships between different parts of a system. By leveraging JSON-LD, DTDL can provide a common structure and semantics for digital twin models, making them interoperable across different systems. This makes integrating different systems in a smart manufacturing environment easier, where you might have digital twins for various machines, processes, and workflows. Here is a simple example to illustrate the concept. In a typical JSON representation, information about a machine might look like this. In this JSON representation, we have basic information about a CNC machine. However, it lacks context and semantics, which can cause interoperability issues when integrating with other systems. In JSON-LD representation using DTDL, the same machine might be represented like this. In this example, add context provides additional semantics for our machine data. At vocab, dtmi.com.example machine1 sets a default vocabulary for terms in our data. The terms last maintenance and output are further defined, linking them to specific definitions in our vocabulary and specifying their data types. Providing these additional semantics makes our data self-describing and easier to integrate with other systems. Sparkplug offers a specification that enables OEM device manufacturers and application developers to build comprehensive and interoperable SCADA or IoT solutions, leveraging MQTT as the core messaging technology. Beyond establishing a structured MQTT topic namespace enriched with semantic properties to ensure interoperability in smart manufacturing, Sparkplug's true distinction lies in its MQTT payload definition, which provides a standardized approach to data modeling through binary message encoding. To enforce interoperability, Sparkplug supports data type definitions for its payload components. These include primitive data types, complex data types via templates, datasets, enhanced metrics with customizable metadata, metrics aliasing for bandwidth efficiency, as well as historical and file data. To illustrate the concept of complex data types using templates, let's consider a manufacturing setting with multiple machines, each equipped with various sensors. These sensors might monitor metrics like temperature, vibration, and energy usage. In a Sparkplug implementation, each machine could be considered an edge of network node, and each sensor could be a device. A template in this context could be a predefined set of metrics that each sensor should report. For example, a temperature sensor's template might include metrics for current temperature, maximum and minimum recorded temperatures, and status information indicating whether the sensor is currently operational. When a new sensor is added to the system, it could use this template to know what data it should report and how that data should be structured. This would ensure consistency across all sensors of the same type and would make it easier to manage and interpret the sensor data. While Sparkplug uses Google's protocol buffers for encoding data, here is a basic representation of a Sparkplug template schema in JSON for the temperature sensor example. In this simplified example, the template for a temperature sensor includes an ID for the device, called device ID, and a set of metrics. Each metric includes a type, a unit, and a description. In SCADA or IoT platforms like inductive automation's ignition, templates are formed by incorporating user-defined types. This process essentially involves publishing models and their instances that reference ignition UDTs into the industrial IoT data infrastructure. These models and instances can then be dynamically utilized by other Sparkplug-enabled applications, facilitating seamless interoperability and data exchange. OPC UA is a set of standards developed by the OPC Foundation for Industrial Information Exchange. It promotes a unified approach for interacting with different data sources in an industrial setting. OPC UA Companion Specifications are guidelines that define how a particular industry, vendor, or group of products should use OPC UA to ensure uniformity and interoperability. These specifications are developed by industry-specific working groups within the OPC Foundation or by external organizations in partnership with the OPC Foundation. They are formulated based on the specific requirements of each industry, taking into consideration the unique data structures and communication protocols involved. In smart manufacturing, OPC UA Companion Specifications are instrumental in ensuring interoperability by providing a common language and set of rules. They enable diverse manufacturing systems, devices, and software applications to communicate and exchange data effectively. For example, the OPC UA Companion Specification for MT Connect, a standard that allows for the organized retrieval of process information from numerically controlled machine tools, defines a set of OPC UA object types that map to the various components and data items defined by the MT Connect standard. For instance, a machine tool may be represented as a hierarchical structure of OPC UA objects representing different components like controllers, axes, or sensors, and these components may have properties or variables representing data items like temperature, speed, or status. This specification ensures that any machine tool that supports the MT Connect standard can expose its data in a way that can be easily understood and integrated into any system and the MT Connect OPC UA Companion Specification. This promotes interoperability and data exchange in industries where machine tools are used. For illustration, below is a very simplified representation of the XML structure defined by the MT-Connect OPC UA Companion Specification. The actual specification includes additional elements such as events, methods, and complex data types to fully represent the capabilities and data provided by the MT-Connect standard. In this structure, the UA object with the node ID ns equals to 1 and s equals to machine tool represents the machine tool. It contains a variable representing its status and another object representing its controller. The controller object, in turn, has a variable representing the program currently running on the controller. The node ID is used by OPC UA to uniquely identify each object or variable in the structure, and the browse name provides a human-readable name for each element. The Asset Administration Shell, conceptualized within the context of the German Industry 4.0 initiative, is a digital representation or digital twin of a physical asset in the production process. An asset administration shell encapsulates all information about an asset, including technical features, functionalities, and lifecycle data. This information is stored and shared in a standardized manner, allowing for seamless communication between different systems. The asset administration shell can be envisioned as an API, exposing the properties and capabilities of a physical asset to facilitate its administration. It offers a suite of services, some generic and others specific, that correspond to the asset it represents. Generic services include identification, configuration, condition monitoring, and events, while specific services encompass the unique capabilities or functions performed by that particular asset. For illustration, let's consider a conveyor belt system in a smart factory. This conveyor belt system could have an associated asset administration shell which acts as its digital twin. Identification. The asset administration shell would include a unique identifier for the conveyor belt system, making it easily identifiable in a complex network of other systems and devices. The asset administration shell would store configuration data for the conveyor belt system. This could include information about the system's capacity, speed, power requirements, and more. The asset administration shell would provide real-time data about the operating status of the conveyor belt system. This could include information about the system's current speed, load, temperature, and other relevant metrics. The asset administration shell would log any significant events related to the conveyor belt system. This could include system errors, maintenance activities, and changes in operating status. The asset administration shell could also provide access to services specific to the conveyor belt system. For example, it could allow a user to adjust the speed of the conveyor belt or to initiate a maintenance routine. The asset administration shell would also maintain a record of the conveyor belt system's lifecycle data. This would include information about the system's design, manufacture, installation, operation, maintenance, and eventual decommissioning. In this way, the asset administration shell for the conveyor belt system would provide a standardized, comprehensive, and easily accessible source of information about the system. This would enable different devices, systems, and users to interact with the conveyor belt system in a seamless and coordinated manner, enhancing the overall efficiency and flexibility of the smart factory. The asset administration shell is typically represented using structured data formats that align with web standards. The specific format can vary depending on the needs and capabilities of the systems interacting with the asset administration shell, but it's often represented in JSON or XML format due to their wide use and compatibility with web technologies. In the case of our hypothetical conveyor belt system, let's consider a simplified example of how the asset administration shell might be represented in JSON format. This JSON object represents the conveyor belt system's asset administration shell. It includes information for identification, configuration, condition monitoring, and events. Specific services are represented as URLs where these services can be accessed. These will typically point to a RESTful API that allow for interaction with the conveyor belt system. Okay, let us have a look at strength and ideal use cases of the 4 data modeling standards we discussed in this video. Digital twin definition language allows for creating models of digital twins, virtual replicas of real-world machines or processes with a focus on capturing relationships, properties, commands, and telemetry. The use of JSON LD helps provide context and semantics, making the data self-describing and easier to integrate with other systems. DTDL is especially useful when you want to model a complete manufacturing line or a whole factory. It allows you to create and maintain a real-time overview of operations, which can be invaluable for decision-making and optimization. MQTT Sparkplug shines in situations where you need to manage multiple machines, systems, or devices, each with multiple sensors. Sparkplug's use of templates for complex data types ensures consistency across all data generators of the same type, facilitating data management and interpretation. Moreover, Sparkplug's emphasis on data type definitions and efficient bandwidth utilization makes it ideal for large-scale operations and cloud connectivity where communication efficiency is paramount. OPC UA Companion Specifications are highly versatile and can be used across various industries. OPC UA excels in environments that use a diverse range of systems, devices, and software applications, since it provides a common language and a set of rules for communication and data exchange. The example of MT Connect demonstrates the benefits of using OPC UA Companion Specifications when dealing with machine tools in manufacturing, as it simplifies data exposure and integration into OPC UA compatible systems. Asset Administration Shell is especially useful when you need a standardized way to manage individual assets within a production process. It can provide real-time data about an asset's operating status, log events, and even provide access to specific services related to the asset. Asset Administration Shell is also helpful for lifecycle management of assets, as it keeps track of data from design and manufacture to operation and commissioning. While each standard has its strength and ideal use cases, they also have areas of overlap and they can complement each other in certain scenarios. For example, Digital Twin Definition Language and Asset Administration Shell both provide a way to create a digital twin of a physical asset. However, DTDL places a strong emphasis on the relationships between different devices, while Asset Administration Shell focuses more on the individual asset and its life cycle. Sparkplug and OPC UA, on the other hand, provide a way to structure data and ensure interoperability. Sparkplug uses MQTT and protocol buffers, focusing on SCADA or IIoT solutions and efficient data encoding, while OPC UA provides a more generalized approach, offering industry-specific guidelines through companion specifications. In a complex smart manufacturing setup, it is conceivable that all 4 standards could be used together. For instance, you might use Digital Twin Definition Language to create digital twin models of your assets, Asset Administration Shell to manage the lifecycle data for each asset, Sparkplug to handle communication between sensors and devices, and OPC UA to ensure interoperability between different systems, devices, and software applications. In part 5 of this series, we explore the pivotal role of MQTT Sparkplug in establishing a robust data infrastructure for smart manufacturing, focusing on the creation of a unified namespace. We delve into the strategic approach required to design the unified namespace data architecture, emphasizing the importance of identifying existing namespaces within the operation technology environment. Thank you for watching and see you in the next video.